In the second week of this course, I told you about heuristic search and the A-star algorithm. Then I showed you how Strip's planning problems can be solved using forward state space search, which implicitly assumed you can use the A-star algorithm for this. But of course, one of the things that A-star needs is a heuristic that tells us how far from the goal a current state is. And that's what we're going to look at in this segment. And we're going to start off by some simple heuristics that can be directly derived from the planning graph we've just seen. Here is a quick recap of one of the things we've already learned about A-star, namely that A-star is optimally efficient. This means that for a given heuristic function, no other algorithm is guaranteed to expand fewer nodes than A-star. This means that if we are given a heuristic function and that function is fixed, we cannot change it, and we insist on having a minimal length solution plan, then there cannot be an algorithm better than A-star that we can use for search. But there are a few caveats. For example, the guarantee that A-star returns a minimal length solution relies on the fact that the given heuristic is admissible. Now, if we don't have an admissible heuristic, then the guarantee doesn't exist anymore. Or, if we don't insist on having minimal length solutions, then we can imagine algorithms that ignore certain parts of the search space, thereby missing certain solutions, but still come up with a non-optimal solution. And you may remember that I told you that A-star still uses exponential memory, so depending on the size of our problem, this algorithm may simply run out of memory, and we need to do something else then. So A-star is not the answer to all questions, but is a very good algorithm for performing search. And there is one way we can improve the algorithm, and that is simply by using a different heuristic function. If we can find a better heuristic function, then A-star will perform significantly better, and that is what we want to achieve. Now, when I showed you the planning graph, I talked a lot about what this graph is doing, namely that it is doing a reachability analysis for our given goal from the initial state. And now I want to see whether we can use this reachability analysis to derive a heuristic that we can use during forward search. And the reachability analysis performed by GraphPlan and encoded in the planning graph looks as follows. We're given a propositional planning problem, and we construct the planning graph consisting of nodes and edges for this problem. Then let us assume that our goal consists of sub-goals g1 through gn here, and then the analysis showed us that for each of these goal components, this goal component is reachable from the initial state if there's a proposition layer pg such that the goal component that we're looking for is an element of this proposition layer. Or we can look at this the other way around, namely if we look at a proposition layer PM, then we can say that if our goal component that we're looking for is not in this proposition layer PM, then that goal component cannot be reachable in m steps. If it was reachable in m steps, then there would be an m-step plan that makes that goal condition true. And that means that plan would have to be part of our planning graph and would add proposition gk to our planning graph in layer PM. But we've seen that it's not in that layer, so there can't be such a plan with m steps. So this gives us an idea how we can define a heuristic for our goal component gk. And that's the heuristic we define here. It's m, and this m, what that is the first layer PM, such that our goal component, gk, is in that layer. Note that we have to choose the first such layer here. So we know that in PM-1, gk is not contained, so it cannot be reachable. But in PM it is contained, so in theory it may be possible to reach the goal condition gk in m steps. So we can use that as a heuristic, and because this is minimal, because we've used the first layer, it is actually an admissible heuristic for this goal condition. Of course, this only works for a single goal condition, not a conjunction of goals. And we've already seen that in a planning graph, we can select multiple actions from one layer. So M often underestimates the number of required actions quite significantly. But it is the best heuristic we've seen so far. And here is our familiar planning graph example that we've used a couple of times now to illustrate this concept of using the planning graph to compute a heuristic. Remember, the original goal we were looking at was to swap the two containers. So we wanted container A at location 2 and container B at location 1. So there's two goal components to this overall goal. And we can compute the heuristic function we've just looked at by looking at the planning graph and seeing where those two goals first appear. And if we look at A2, it's already circled in red here, because at first it appears in proposition layer P3. And we can look at this, is not in this layer, not in this layer P2, and it appears here for the first time. And similarly, B1 appears here for the first time. So what we have is that the heuristic we've just defined for A2 is 3, because it takes at least 3 actions to make that proposition true, and we know that from looking at the planning graph. And the same applies for B1. It takes at least 3 actions to make this proposition true. But note that we have said nothing about which actions these are. So these actions will be from the 3 action layers, but for all we know, they might be the same 3 actions for both goals. So that is a problem. How do we combine these two values into a single heuristic for a composite goal? So the question is, how do we combine the information gained from the planning graph as a heuristic for individual goal conditions when we have multiple goal conditions? So we are given a planning problem, but our goal consists of more than one goal, G1 through Gn, and we need to combine the heuristic values for the individual goals into an overall heuristic value. And there are 2 obvious ways in which this can be done. The first option is we simply take the maximum. So this option assumes that the actions that we need to achieve all the goals overlap significantly, and therefore taking the maximum will tell us how long it will take in the worst case to achieve all the goals. The advantage of this approach is that the heuristic is still admissible, so it was admissible for each individual goal, but now taking the maximum gives us an admissible heuristic for all the goals. In practice, it turns out that this heuristic is very inaccurate, and the problem comes when we have independent goals. For independent goals, the actions we need to achieve these goals often don't overlap much, in which case this heuristic badly underestimates what it takes to get to the goal. The second obvious option, instead of taking the maximum, would be simply to add all the values for the individual goal and combine them in this way. So the first drawback of this is that this approach gives us no longer an admissible heuristic. This may well overestimate the distance to the goal because there are shared actions, and they often are. And if we don't take this into account, we count these actions multiple times when we compute our heuristic. And that means this heuristic becomes quite inaccurate for dependent goals. Now you could ask, are dependent goals very realistic? And in many domains, unfortunately, they are. Think back to what relations we've defined for the dog worker robot domain. There is the at relation that tells us where a robot is, and there's the occupied predicate that tells us whether a location is occupied or not. These two are always dependent. If they both appear in a goal, then just adding the values to achieve the two doubles the amount of effort that we estimate. But at least we now have 2 heuristics we can use to apply A* to forward state space search. And one thing to note for both of these heuristics, which is quite interesting, is they're based on the planning graph, but neither of those really requires the computation of the mutex relations. So we could use them in a planning graph with or without mutex relations, meaning we actually have 4 different heuristics already.